Hello students, today I will discuss about the last part of chemical kinetics and I will discuss it from NCERT of your chemistry text. Temperature dependence of the rate of a reaction. Most of the chemical reactions are accelerated by increase in temperature. For example, decomposition of N2O5 at 50 degrees centigrade takes 12 minutes for half life, 12 minutes for half decomposition, 5 hours at 25 degrees centigrade and 10 days at 0 degrees centigrade. So it has been found that for a chemical reaction with rise in temperature by 10 degree, the rate constant is nearly doubled. This is explained by Arrhenius and it is governed by Arrhenius equation as K equal to A into e to the power minus EA by RT, where A is Arrhenius factor or the frequency factor. It is also called pre-exponential factor. It is a constant specific to particular reaction. R is gas constant and EA is activation energy measured in joules per mole. It can be understood clearly using the simple reaction H2 plus I2 gives 2HI. Formation of HI through the intermediate. According to Arrhenius, this reaction can take place only when a molecule of hydrogen and a molecule of iodine collide to form an unstable intermediate, as in the figure. It exists for a very short time and then breaks up to form two molecules of hydrogen iodide. As you know, the energy required to form this intermediate called activated complex is known as activation energy, figure in the side, is obtained by plotting potential energy versus reaction coordinate, that is time. The reaction coordinate represents the profile of energy change when reactants change into products. Some energy is released when the complex decomposes to form. Reaction depends upon the reactants and products. All the molecules of the reacting species do not have same kinetic energy, since it is difficult to predict the behavior of any one molecule with precision. According to Maxwell-Boltzmann used statistics to predict the behavior of large number of molecules. According to them, the distribution of kinetic energy may be described by plotting the fraction of molecule with a given energy versus kinetic energy. Hence, the graph distribution curve showing energy along gaseous molecule. When temperature rises 10 degree, the graph flattens forward and shows an increased area for energy of activation, higher energy of activation to go for reaction. The increasing the temperature of substance increases the fraction of molecules which collide. The energy is greater than EA. It is clear from the diagram that the curve T plus 10, the area showing the fraction of molecules having energy equal to or greater than activation energy gets doubled, leading to doubling the rate of reaction. Now, mathematically, ln K equal to minus EA by RT plus ln A. The plot of ln K versus 1 by T gives a straight line according to equation given in figure 4.19 as shown in figure 4.10. Thus, from this we get slope equal to minus EA by R and intercept equal to ln A. So we can calculate EA and A using these values. At temperature T1, ln K1 equal to minus EA by RT1 plus ln A. At temperature T2, equation is ln K2 equal to minus EA by RT2 plus ln A. Subtracting these two values, we get ln K2 minus ln K1 equal to minus EA by RT1 minus EA by RT2 into T2. That gives ln K2 by K1 equal to EA by R into 1 by T1 minus 1 by T2. Hence, ln K2 by K1 equal to EA by R into 1 by T1 minus 1 by T2 equal. So, log K2 by K1 equal to EA by 2.303 R into 1 by T1 minus 1 by T2. Now, we will use this equation for calculation of A, EA and K. Examples given. Now, effect of catalyst. A catalyst is a substance which increases the rate of a reaction without itself undergoing any permanent chemical change. For example, MnO2 catalyzes the following reaction so as to increase its rate considerably. 2KClO3 in presence of MnO2 gives 2KCl plus 3O2. The word catalyst should not be used when the added substance reduces the rate of reaction. The substance is then called inhibitor. The action of the catalyst can be explained by intermediate complex theory. According to this theory, a catalyst participates in a chemical reaction by forming temporary bonds with the reactants resulting in an intermediate complex. This has a transitory existence and decomposes to yield products and the catalyst. See the graph. It is believed that the catalyst provides an alternative path or reaction mechanism by reducing the activation energy between reactants and products and hence lowering the potential energy barrier as shown in the figure. It is clear from Arrhenius equation that lower the value of activation energy, faster would be the rate of reaction. Now, collision theory of chemical reaction. Though Arrhenius equation is applicable under a wide range of circumstances, collision theory, which has developed by Max Truss and William Lewis in 1916 to 18, provides a greater insight into the energetic and mechanistic aspects of reaction. It is based on kinetic theory of gases. According to this theory, the reactant molecules are assumed to be hard sphere and reaction is postulated to occur when molecules collide with each other. The number of collisions per second per unit volume of the reaction mixture is known as collision frequency Z. Another factor which affects the rate of chemical reaction is activation energy. For a bimolecular elementary reaction, A plus B gives products. So, rate of reaction can be expressed as rate equal to ZAB into e to the power minus EA by RT, where ZAB represents the collision frequency of reactants A and B, and e to the power minus EA by RT represents the fraction of molecules with energies equal to or greater than EA. Comparing the Arrhenius equation, we can say that A is related to collision frequency. When ZAB represents the collision frequency of reactants A and B, and e to the power minus EA by RT represents the frequency of molecules with energies equal to or greater than EA, comparing the Arrhenius equation, we can say that A is related to collision frequency. Equation predicts the value of rate constant fairly accurately for the reaction that involve atomic species or simple molecules, but for complex molecules significant deviations are observed. The reaction could not be that all collisions do not lead to the formation of products. The collision in which molecules collide with sufficient kinetic energy, called threshold energy, the proper orientation so as to facilitate breaking of bonds between reacting species and formation of new bonds to form products are called effective collision. For example, formation of methanol from bromoethane depends on the orientation of reactant molecules, as in the figure. The proper orientation of reactant molecules lead to bond formation, whereas improper orientation makes them simply bounce back and no products are formed. Hence, the new factor, probability factor or steering factor, should be introduced. So, rate equal to P into ZAB into e to the power minus EA by RT. Thus, in collision theory, activation energy and proper orientation of the molecules together determine the criteria for an effective collision and hence the rate of a chemical reaction. Now, this is the last part of this chapter. Now you must practice the in-text question. Thank you for watching my video. Please give your feedback in the comment section. Thank you very much.